Hello everybody, welcome back to another video lecture. Today we're going to be talking about section 1.2, and we're going to specify, we're going to talk about using functions. Okay? I think the actual title of this homework is called Representing Functions, but the overall goals are going to be the same. So first we want to define some functions. So the first thing that I want to talk about is I want to talk about a classification of functions that are called polynomials. Poly coming from the Greek, multiple, nomial meaning number. And a good way to write a polynomial is that we have a coefficient, which is just a known number, times a variable. We usually choose x to be the independent variable, to a particular power n. And we can add more and more of these, getting smaller and smaller as we go until we add a squared term, a linear term, and a constant term. Okay, so any polynomial you have is built mainly through understanding what are its coefficients and what are its powers. And I will point out, a lot of the coefficients turn out to be zero. It turns out the highest term that we actually see there, what we sometimes refer to as the leading term, defines the polynomial in a very specific way. Okay, so what we call the leading term the term that contains the highest power. Okay, and that highest power we usually refer to as a degree, or the degree of the polynomial. Now, we get some names for these polynomials based on their degree. So if we go a degree 1 polynomial, for example. Now, I am going to write down 0, but I don't want to start with 0. Here is an example, just writing out one. So 3x plus 4. See, we have the leading term, 3x, whose highest degree is 1. Notice we omit the 1. All of these have names. For example, we call a degree 1 polynomial, we call it a linear function. A degree 0, we call it a constant function. Notice, even though it's still there, I am not writing the x to the 0 because overall x to the 0 just equals 1. So we actually get to omit that pretty much for free. As we move on, we have degrees 2s. Please note, we can write these in whatever order we want. We can write these in whatever order we want. The leading term is not necessarily the first term, even though in this polynomial, the 6x is written first. That does not make it the leading term. The leading term is whatever term contains the highest order. And in this case, that would be negative x squared. We call that a quadratic. I'm going to stop writing the examples, but just to give off some more, we have degree 3s are called cubic polynomials, and degree 4s are called quartic polynomials. And that's pretty much where the naming convention ends. We don't usually name those degree 5 polynomials any further. Now, based on our polynomials, one really nice thing is all polynomials are functions which means they all take each input into one and only one output. And something else that's nice, all polynomials have domain, and the domain is all real numbers. Now you can write this a couple different ways. This kind of fancy looking R symbol, that's another way of representing R. Or what I call R is the set of all real numbers. In our notation, we usually just say it starts at negative infinity and it goes until infinity. Okay? So, we're going to dive into some linear functions. And it turns out there's several different ways to write down these linear functions. The one you're most familiar with is probably slope-intercept form. Now, slope-intercept form is the specific form y equals mx plus b. Keep in mind, even though I'm writing y, we can always replace y in f of x. It's just a notation convention. Where specifically, we refer to, going back to my red, we go m is the slope and b is what we call the value of the y-intercept. And these act like, identifiers for our functions. Once we know the slope of a function, we know its intercept, we kind of know what the function is. So going as something that I can draw, let's say I have this function, I'll call this maybe 0, 1, and I'll call this point maybe 8, 4. And let's say we have some function connecting those 2 points. And the question is, can I determine what that function is? And the answer is, if I can determine the value of the y-intercept and the slope, I can. So, first things first, the slope, it is the change in y divided by the change in x. There's this some amount of what I would call a vertical change, and there's also a horizontal change. We just need to count that up and figure out how much it is, and that's what this equation does for us. Specifically, I call this x1 and y1, and I'll call this x2 and y2. And what you can see is y2 minus y1 divided by x2 minus x1, 3 over 8. And there is our slope. The slope of the line that connects these two is going to be 3 divided by 8. Now, what is b? Now, I will point out, some of you are like, oh, this point just happens to be the y-intercept. And that is absolutely true. But you don't have to rely on that. There's an equation that we can actually just plug in. And you can plug in what you call y1 or x1 doesn't actually end up mattering. But if we plug in this coordinate right here, you're going to see b is 1 minus the slope times 0, which gives me that b was equal to 1, which you could just see, but it's nicer to actually work it out. And so with these two things together, I have a slope, I have a y-intercept, I can write the equation of this line, y equals 3 over 8x plus 1. And that is the equation of this line. So, as long as you can determine the slope and the intercept, you in a way have determined the line. But it's not the only form that a linear function can take. For example, there is also what is sometimes referred to as, hilariously, standard form. Standard form is where you group x and y on the same side. And this is a very historical notation. If you do anything in the business world, you'll see a lot of this. Now, there is one more trick is that you don't want, so taking it from slope-intercept form, you don't want any denominators. I'm actually going to end up multiplying this by negative 8. So what you get is 3x minus 8y equals negative 8. This line and this line are identical. It's just their presentations are slightly different. Now, we're going to operate mostly in slope-intercept form. In fact, most of what you're going to have to do is take something that looks like this and rewrite it as something that looks like that. But you can do that just by solving for the y term. Minus the 3x, divide by negative 8. Those standard algebra rules that we can get. Now, still technically a linear function. We can also talk about something that is called a piecewise function. Now, this is where we want the function to behave differently at different places. So, here's an example of a piecewise function. So this is the function that's going to behave like, and I'll make it a little bit more complicated. It's going to behave like 2x when x is less than 3. And it's going to behave like negative x for x values that are greater than or equal to 3. So, for example, what is f of 1? Well, 1 less than 3, we're going to plug it into this one. We should get 2 as an output. What is f of 5? Well, 5 is not less than 3. We're going to get negative 5 as our output. And this is still, presumably, it's a function, although it's a more special function. Let's see if we can't draw this one. I'll be honest. I don't know if I'll be able to. So, right at 3, we know it should behave like negative x, which means it's definitely going to respond with negative 3, right? F of 3 is going to be negative 3. But if we were on this other end, if we look at, let's say, f of 2 as well, just kind of sneaking this one in, f of 2 behaves like 4. F of 1 behaves like 2. Assume f of 0 looks like 0. And you see we have this line with a slope of 2. And it's heading off, it's heading off, it's heading off. And then right at 3 it's going to change. So what's happening to this left-hand side, we write this little open circle that says, hey, this is the termination point. This is where this part of the line is heading. But of course it will never get there because the functional rules can only allow one output. So we do this open line there, and then we have this hard line, this filled in dot, that tells us our work there. And I think that's going to continue a little bit like that. So this is our piecewise linear function. And it turns out, they're pretty far away from each other. Sometimes they're closer, sometimes they touch exactly, but this is not one of those times. So the important thing is to figure out, before you go plugging in, you have to figure out your input, where does it line here? And we can do as many or as few of these piecewise functions as we want. Just remember that anything that uses a less than or greater than symbol without that equals, that's going to be an open circle. Anything with the greater than symbol will turn out to be a filled in circle. Okay? Piecewise functions are not something we talk a lot about, but we will talk about them just ever so slightly. Okay. Now, before we make a jump into studying some different functions, I want to talk about what the idea of a function transformation. Okay? So, this is our start. We want to ask ourselves, what happens if we do something like, instead of f of x, what if we multiplied it by 3? What if we subtracted 5? What if we added 1 inside the function? That's what we want to take a look at, is what happens as we start to do these things. So, in order to better help you this, my drawing ability is somewhat limited. I'm just going to go to our graphing calculator, and I'm going to write just some functions. So here's f of x, which is going to be, for right now, we'll do a fairly basic one, just a simple quadratic in red. Okay? Now let's do f of x, and let's start adding in this constant c. Okay? So right now I have the source or the start function in red, and in blue I am adding a c term to the outside of the function. And as I let this start to move around, it disappears, it comes back. You can see that this additional outside constant has what we would call a vertical translation. And I'll write this down in a second after we do some more exploring. But we have this vertical translation going on. So anything that you put on the outside, the overall effect is, what's the difference between the red x squared and the blue x squared plus 3.1? It has been increased, vertically translated by about 3.1. What happens if we put the c on the inside? Well, we do still see a translation. It's not vertical, though it is horizontal. Now, something that's a little bit interesting, that's something students struggle with, is if you'll notice, this translation is not in the same way. Last time when we added 3.1, it moved up 3.1, and we have that association that positive things go up. Right now, let's say we're adding 3.1, but it didn't move where I was expecting it to. I was expecting that when I added 3.1, it would increase it to the right. But it turns out anything that happens on the inside of the function notation, this horizontal translation is a little bit backwards. Okay? What the right direction is, or what I should say the increased direction, is actually towards the left, which is, it's just one of those things that it seems like it should work out, but understandably, mathematically, it does not. So these are our translational terms. We also have something that we call the scale factors. Now we can start doing some multiplication. But reminder, we can also multiply on the inside and outside. So this outside multiplication, you can see, it scales us up. Notice our positive numbers, they have this sharpening effect, right? As the number gets larger and larger, it seems to be sharper and sharper. Now, when we dip below 1, now we're in what I would call a fractional territory. We get this widening effect. Once we get to 0, we're kind of out. But then we come back in that same idea, but now we've just reflected. Okay? And we call this a stretching, but we call this a reflection, specifically an x-axis reflection. We're reflecting over the x-axis. Now, since you know what we did with the vertical translation, if we go on the inside, we also see pretty much the exact same thing for this one. Now, this one is not the same, but notice, we don't seem to be getting that reflection. But in reality, we are. I'm going to switch this power to being cubed. And now, you can kind of see what reflection is happening. You're still seeing that stretching and that, pointing, curving. But now you're seeing this y-axis reflection when that c goes negative, right? Not only are we stretching, we're getting sharper, more pointed, because the value is greater than 1, but because it's negative, we're reflecting over this y-axis. We just couldn't see it, because when you reflect x squared over the y-axis, you get the same thing. But in reality, you could argue that the sides have shifted, which I just think is interesting. Okay, let's go back and let's sum some of our functional translations up. Okay, now typically we like to write things like, or it's somewhat standard to write something like this. F of x minus h plus k. And what this is telling me is this h is my horizontal translation, and this k is my vertical translation. Now, why the negative? Well, because we really like it when there's a 3, when h is 3, that means move to the right 3. But in order for that, we really need it to be x minus 3. So, just as a quick, sort of demonstration, let's talk about a function that we haven't seen. Let's say that f of x equals 1 over x. And I'll give you a hint that it looks like this with some asymptotes. Okay? Sorry that my drawing surface got curved. Okay? Now, what is this going to look like? Well, this is 4 units to the left, and that's 9 units, what I would call down. So, taking the same structure, moving it 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my new 0, 0. I think it's going to look like that. And this is actually, hopefully, something that we can kind of see if we go 1 over x and we specify f of x minus 4 plus 9. Whoops, I made the same mistake that I warned you guys on making. Wait, did I do plus 4 or minus 4? Oh, x plus 4. Minus 9. All we've done is we translated the red 4 units to the left and 9 units down. So that's something that we use quite a bit, just to kind of, as long as you understand what the the start function looks like, a lot of these transformations you can just kind of make educated guesses about. Oh, is it a reflection? Oh, is it something else? Okay, so I wanted to work a question from the homework with you, just because I think that's interesting. So I'm bringing in this one. This is from section 1.2. Find the points of intersection for the parabolas y equals x squared and y equals negative x squared plus 22x using analytical methods. Use a graphing utility to check your own work. So the question is, sorry, I'm actually going to pull that up again. I'm going to have it all open on my second monitor just so I can remember the numbers. The question is, where does y equal x squared and y equals negative x squared plus 22x intersect? Now, this is a problem that you can solve using graphical methods, and that's absolutely fine. But it says that we should try it using analytical methods, and then we'll use a graphical to check our work. So what does it mean to intersect? Well, graphically, what it means to intersect is if we have 2 different curves, you and I will hopefully all agree that anywhere those curves overlap is where they intersect. Now, what does it mean to intersect analytically? Well, these are what we call the analytical descriptions. These are not pictures per se, but they contain the same information. And what they mean is there are x and y pairs that are the exact same for both of them. So essentially, it's saying that x's are equal to x's and y's are equal to y's. But we actually have 2 different descriptions for y. This left-hand function tells us that y is x squared, and the right-hand function tells us it's negative x squared plus 22x. So the question is, for what values of x does this thing become satisfied? How can we find that? Well, we're going to solve it. How are we going to solve it? Let's grab, I like to use different colors. Let's move everything to one side. I'm going to add x squared to both sides. I'm also going to subtract 22x from both sides. So x squared plus an additional x squared is going to give me 2 of them, minus a 22x. All of that equaling 0. Okay? What else can I do? Well, I can actually do what is sometimes called factoring. It's kind of like dividing out what they share. So, what does this term and this term share together? Well, they both definitely have a 2, and they both definitely have an x. Okay? So, if I took away that, if I took away the 2 and I took away one of the x's, I'd be left with one of the x's. Versus, if I took away a 2 and an x, I'd be left with an 11. Now, this is a very important property in mathematics called the zero product principle, which essentially states that anytime you have a set of things multiplied and equal to 0, at least one of them individually has to be equal to 0. What are two numbers that multiply to equal 0? 3 times 0. 4 and 0. Negative pi squared over the square root of 13 and 0. Those are the only ways to get these things equal to 0. So, there are 3 choices. Either 2 could equal 0, and it doesn't. X could equal 0, that's a choice. Or x minus 11 equals 0. Well, this one we can do a little bit further. If we add 11 to both sides, that's the same way as writing that x equals 11. So, I see 2 solutions, and I'm going to grab a really horrible piece. Where does x squared and negative x squared plus 22x, where do those things equal each other? I find 2 values, x equals 0 and x equals 11. But reminder, that's just where the y's were equal to each other. We also want to find the x's equal to each other. So we can actually plug that in. So we're going to plug into the simpler one. If we plug both of these values into here, we get that I'll write it underneath. Y is equal to 0 squared, which is 0, or y is equal to 11 squared, which is 121. Final answer. Where do y equals x squared and y equals negative x squared plus 22x intersect? I see 2 answers. I'm going to give them to you in coordinate form. I think 0, 0, and 11, 121. Those are going to be my answers. Now, I'm going to type those answers in to MyLabs as 0, 0, additional comma, 11, 121. Hopefully it thinks I'm right. It does think that I'm right. Let's use a graphing utility just to make sure that that actually does work out the way that I was expecting. And this is where you can use a graphing calculator. I think that's great. I like to use Desmos just because I think it's the prettiest graph. If we do x squared as 1, and we do negative x squared plus 22x, we can see one intersect point right at 0, 0. It's where the purple line is traveling through and the red line is traveling through. And what about this other one? Kind of got to move around the page. But you can see right here, the black line goes through it, the purple line goes through it, 11, 121. If we scroll out, we might be able to get both of these at the same time. So, I think we were able to find them. Okay, as a review of what we were able to cover, what we were able to talk about, remember, we have functions that we're interested in manipulating, and that's really where we're starting right now. And you should be very comfortable, and hopefully you have the ability to solve some of these things together, setting things equal to each other. Reminder, what we can do on either or both sides. And if you feel like you're still lost on the homework, please send me an email. Let me know. It's my job to make sure that you are as prepared as you can be. And so if you have any questions, feel free to ask. I'd be happy to do what I can. I'll see you guys in the next video.